Three-terminal device. The three-terminal device circled in figure is an NPN transistor. So this transistor is an NPN transistor. It works using three simple rules. Number one, the net current into the device is the same as the net current out of the device, so that IC plus IB is equal to IE. This is actually collector current, base current, and emitter current. Number two, the potential at point E is always 0.6 volts less than the potential at point B. So there is a voltage drop between B and E, 0.6 volts. Thus, V in minus VE, so V in is, if the switch is connected, V in is the voltage at point B, V in minus VE is 0.6 volts. The third rule, the current into point C, which is the collector current, IC, is always a fixed multiple of the current into point B, the base current, IB. IC is beta times IB, where beta is much greater than 1, is a parameter characteristic of the transistor. Use these rules to answer the following questions. Part A. What is the potential V out? The potential of point C with respect to ground in terms of V in the limit beta becomes infinite. And there is a hint, determine the emitter current IE in terms of V in and use this to determine IC in terms of V in and beta. So first I will determine the emitter current in terms of V in and beta. And I will use that to find IC in terms of V in and beta. So this is going to allow me to calculate the voltage drop here, and basically subtracting this from 15 volts, I will obtain the voltage of point C. The potential difference across the 1 kilo ohm resistor can then be used to determine V out. Take the limit beta goes to infinity in this result. Okay, so I'm going to start with a Kirchhoff voltage law, KVL1, for this loop here. And you can see that I have this emitter current flowing through this. So this is plus, this is minus 100 times IE minus V in, because I'm encountering the minus terminal here, minus V in. And then plus VBE, the potential of B with respect to E, which is 0.6 volts. This should add up to 0. So I'm writing in part A, KVL1 equation, 100 times the emitter current minus V in plus potential of B with respect to E is equal to 0, knowing that potential of B with respect to E is 0.6 volts. That was rule number 2. And IC, collector current, is beta times the base current. That's rule number 3. So the emitter current, IE, can be written as the input potential V in minus 0.6 volts divided by 100. And at the same time, rule number 1 tells me that IC plus IB must be equal to IE. Collector plus base current is emitter current, and collector current plus collector current divided by beta, which is the base current, is the emitter current. And this tells me that as beta goes to infinity, the collector current is equal to the emitter current. Okay, now I'm going to write Kirchhoff voltage law 2 for this whole loop here. So let's do that. KVL2. Now you can see that starting here I have 1000 times IC plus the output voltage Vout minus 15 is 0. So 1000 collector current plus the output voltage minus 15 is 0. That's basically a simple loop. So this tells me that the output voltage that I'm after is 15 minus 1000 times the collector current. This is 15 minus 1000 times the collector current I have found using KVL1 V in minus 0.6 divided by 100. Let's check that result here. V in minus 0.6 divided by 100 is the emitter current, but emitter current is the collector current as beta goes to infinity. So that's what I have substituted here. So this gives me 15 minus 1000 divided by 100 is 10. 10 V in plus so this is going to give me 10 here minus 10 V in, and minus minus will become plus 6 volts, and that will give me the output voltage as 21 minus 10 times the input voltage. This is basically the question in part A. What is the potential V out in terms of V in the limit beta goes to infinity? Part B, what value of V in is needed so that V out is 7.5 volts? While using this equation, V in is 21 minus V out divided by 10. So I'm isolating V in here. So V out we want to be 7.5 volts. In that case, V in will be 21 minus 7.5 divided by 10. So we find that V in should be 1.35 volts. For V out to be 7.5 volts, V in has to be 1.35 volts. Now let's look at part C of the problem. If the input potential includes a small time-dependent signal so that V in is 15 volts plus V in as a function of time, then the output potential is V out equals minus 129 volts plus G times V in T, where G is a gain factor. What is G for this circuit? Now I have the input voltage V in given as 15.0 volts plus V in time dependent part, and V out is minus 129 plus G times the time dependent part of the input voltage. Now V out is 21 minus 10 V in, so it's going to be 21 minus 150 minus 10 V in of T, which is minus 129 minus 10 V in of T. So this tells me that the value that I'm after, G, must be equal to minus 10. Basically, I have used this relationship between V out and V in and found that the gain factor should be minus 10. So in this problem, we have a three-terminal device, the NPN transistor, which is subject to three rules. The currents entering the transistor adopt to zero. IC plus IB is equal to IE. The collector current is beta times the base current. So that was rule number 3, where beta is much greater than 1. And there is a voltage drop of 0.6 volts between the point B and point E when the switch is closed. So we're basically assuming that the switch is closed. Under these conditions, what is the relationship between V out and V in? So first of all, I write Kirchhoff voltage law for this loop here. I see that I have 1000 times let's see, Kirchhoff voltage law is 100 times IE, that is this one, minus V in plus VBE, which is 0.6, is equal to 0. So that gives me IE is V in minus 0.6 over 100. IC plus IB is IE, but IB is IC divided by beta. If beta is infinite, IC is equal to IE. So I write Kirchhoff voltage law 2 here for this loop. 1000 IC plus V out minus 15 is equal to 0. So that's this loop. And V out is 15 minus 1000 IC. For IC, I substitute IE, which is V in minus 0.6 over 100. And this allows me to write V out as 21 minus 10 V in. Substituting V out 7.5 volts, I find that V in should be 1.35 volts. If V in has a time dependent part, it's 15 plus V in of t, then I can see from this equation that V out will have a time dependent part. It will be minus 129 minus 10 times V in of t. And V out is minus 129 plus G times V in of t. The gain factor G then should be minus 10.